When a truly massive star runs out of fuel, it doesn't just fizzle out. It dies in this spectacular, universe-shattering event. But what's really going on in its final moments is this titanic struggle, a cosmic battle between two of the most powerful forces in nature. So let's dive right into this battle for the very soul of a star.
Right, because think about it. Once those nuclear fires that have been pushing outward for millions of years finally go out, what's to stop gravity's relentless crush from just squeezing the star down to an infinitely small point? And yet, for a lot of stars, that's not what happens. So the question is, what mysterious force steps into the ring to fight back?
Okay, first, let's give some respect to the undisputed champion of the universe, gravity. With the star's internal engine shut down for good, this inward-pulling force is now completely unopposed. It is finally off the leash, and it begins to crush the star's core with just unimaginable power. Yeah, for its entire life, the star was in this perfect, delicate balance called hydrostatic equilibrium. You had the outward push from nuclear fusion perfectly canceling out the inward pull of gravity. But now, the fuel's gone. That outward push vanishes. It really looks like gravity is about to win, and the collapse is on.
But just when it seems like all is lost, a new hero emerges from the truly bizarre world of quantum mechanics. It's this strange, incredibly powerful pressure that has nothing to do with heat, and it basically looks at gravity and says, "Not so fast."
So at the heart of this new defense is a fundamental law of nature called the Pauli exclusion principle. Now this rule applies to a class of particles called fermions, and for our story, the key players here are electrons. And the principle is simple, really. These particles are profoundly antisocial. They absolutely refuse to be in the same state in the same place. And this one little rule is about to become gravity's biggest nightmare.
Honestly, the best way to picture this is to think of a cosmic parking garage. Gravity is the frantic parking attendant, desperately trying to cram an infinite number of cars, our electrons, into a garage with a limited number of spots. But the electrons, they're following Pauli's rule. They refuse to share. So to avoid being crushed into the same spot, they're forced to jump to higher and higher energy levels. It's like they're revving their engines and racing to the top floors of the garage.
And this is what our parking garage looks like to a physicist. Each of these lines is a distinct energy level, a parking spot. And just like a real parking spot, you can only fit so much in there. In the quantum world, that means only 2 electrons can occupy each level, and they have to have opposite spins. So as gravity keeps squeezing, it forces the electrons to fill these levels up, from the bottom, creating this tower of incredibly energetic, zippy particles.
So you have all these high-energy electrons, right? They're all zipping around, pushing back, refusing to be crushed together. And all of that resistance creates a powerful, powerful outward push. Now this isn't pressure from heat, remember, it's a purely quantum effect. And it has a name, electron degeneracy pressure. This is our first shield against gravity.
And for stars up to a certain mass, this quantum shield is more than strong enough. It successfully stops gravity's collapse dead in its tracks. And what's left behind is this incredibly dense, Earth-sized stellar ember, a white dwarf. So round 1 goes to the quantum world.
But what if the dying star is more massive? Well, it turns out our first quantum shield has a breaking point. There is a very specific limit to how much weight it can actually hold. Now check this out, because this is where things get really weird. This graph shows that for these degenerate objects, when you add more mass, they actually get smaller. The increased gravity just squeezes them down even tighter. But look at the top of the curve there. It peaks, and that peak suggests that there's a maximum mass a white dwarf can possibly have before something gives.
And here it is. This is the magic number, known as the Chandrasekhar limit. If the star's leftover core is more massive than 1.44 times the mass of our Sun, electron degeneracy pressure fails. Utterly. The shield breaks, and the collapse begins all over again, but this time with even more ferocity. So gravity is back in the driver's seat, and the collapse is on again. But the universe, well, it has another trick up its sleeve. As that core is crushed beyond the limits of a white dwarf, an even more powerful quantum shield is forged in the chaos.
Okay, so here's what happens. The pressure becomes so intense, so unbelievably high, that electrons are literally forced inside of protons. They merge, canceling out their charge and turning them into neutrons. This process is called electron capture, and it transforms the entire stellar core into a city-sized ball of pure neutrons, basically a giant atomic nucleus.
And this new object is a neutron star. Now it's held up by the same quantum rule as before, the Pauli principle, but this time it's the neutrons, not the electrons, that are pushing back. And the difference is just staggering. We've gone from an object the size of the Earth to one the size of a small city, with a density so insane that a single teaspoon of it would weigh 100 million tons.
So now we have two possible endings for a star: white dwarfs and neutron stars. But there's one final rule we have to consider. To actually exist out there in the universe, a star can't just be in balance. It has to be stable.
You know, the concept is actually pretty simple when you think about it this way. A stable star is like a ball sitting at the bottom of a valley. If you give it a little nudge, it'll just roll back and forth and settle back where it started. But an unstable star, that's like a ball perched right on top of a hill. The slightest push, the tiniest nudge, and it's gone. It's either going to roll away and expand into nothing or collapse completely.
And what this means is that only those stable ball-in-a-valley configurations can actually survive and exist in our universe. All those other ball-on-a-hill solutions, they're just theoretical ghosts that physics simply forbids from existing for any length of time.
Okay, this chart right here is the whole story. This is the master map of what's possible. On the vertical axis, you've got the star's mass, and on the horizontal, you've got its radius. The solid lines represent the families of stars that can actually exist because they are stable, and those dotted lines, those are the unstable ghosts.
Let's just trace the path here. The solid curve that goes from A up to B, that's our family of stable white dwarfs. Then there's this gap, and then the curve picks up again from C to E. That's the family of stable neutron stars. That gap between B and C is a forbidden zone. No stable stars can exist there. And critically, notice that the neutron star line also has a peak, at point E. Anything more massive than that is also unstable and doomed to collapse.
And the coolest part? This isn't just theory. We actually see these things out in space. Pulsars, for example, are these rapidly spinning neutron stars that sweep beams of radiation across the cosmos, kind of like a lighthouse. They are the definitive observational proof that this epic battle between gravity and the quantum world is really happening all across our universe.
Which brings us to our final lingering question. We've seen the first quantum shield, electron degeneracy, fail. And now this map shows us that the second, even stronger shield, neutron degeneracy, also has a breaking point. So what happens when a dying star is so massive that even this final opponent is overwhelmed? What happens when gravity finally and truly wins?